Welcome to day 4. So let me introduce again Professor Witten, who will give his second talk on Fermions and Topological phases.
Thank you. Well, good morning, everyone. So yesterday we were talking about vile fermions. Do we want some of the lights off, actually? Do you dim these lights?
Oh, yeah, sure.
So yesterday we were talking about vile fermions in condensed matter and boundary localized states that they produce. So it's also possible to get boundary localized states from Dirac fermions. And since this is important in understanding topological insulators, I'll say a few words about it. So if we don't have discrete symmetries and don't tune any parameters, then in condensed matter physics it's not natural to have massless Dirac as opposed to vile fermions. This is simply because for a 4-component fermion field that has both chiralities, mass terms are possible. In fact, the relativistic Dirac equation involves 2 mass parameters, which I've called M and also M prime gamma 5, either of which produces a gap. So to get a massless fermion, we need to have a reason that both parameters are 0. So it turns out it's actually possible to achieve this in the context of a crystal with suitable discrete symmetries. But unfortunately, I won't have time to explain this. So the only symmetry I'm going to assume is time reversal symmetry, and that's enough to set one of the 2 parameters to 0, but not both. So the parameter I called M prime is odd under time reversal, but M is even. So in a time reversal situation, the Dirac equation will look like I've written. Generically, M isn't 0, but of course, if we adjust one parameter, that might be, for instance, the chemical composition of an alloy, we can hope to pass through a point where M is 0. So, as a function of some parameter, we could hope to get, with no lattice symmetries except time reversal, a quantum phase transition with a massless Dirac fermion. It turns out that this is the phase transition between an ordinary insulator and the topological one. And so, for now, let's consider a sample with boundary and look for mode localized near the boundary. So, as yesterday, I'll take the boundary to be at x1 equals 0. So, for example, this line here could be the surface x1 equals 0, and the crystal is for positive x1. And we take the natural Dirac boundary condition where I gamma 1 psi is psi. I could change the sign, but that doesn't matter. But what is important is that the boundary condition isn't going to change when the mass passes through 0. In continuum theory, we just pick a boundary condition. But in a condensed matter model, we would have some kind of lattice system, and we would deduce what the boundary condition is by analyzing how to pass from the discrete model to a continuum approximation. Whatever is the procedure by which we would deduce the boundary condition from the lattice model isn't sensitive to the mass when the mass is small, simply because to decide if the mass is positive or negative, you have to look many, many lattice spacings away from the boundary. Whereas to determine the boundary condition, you would just analyze what's happening near the boundary. So in our phase transition, M will change sign, but nothing will happen to the boundary condition. Now, I will let x parallel be the coordinates along the boundary, which means x2, x3, and time. And what I call ID slash parallel is the part of the Dirac operator that only involves derivatives along the boundary. So now, just as yesterday, we won't write the general solution of the 3 plus 1 dimensional Dirac equation. We'll just write down an interesting solution. The interesting solution has an exponential dependence on x1, with the mass being the exponent. And then it multiplies some function of the boundary coordinates, which I'm calling x parallel. And this boundary function obeys I gamma 1 psi equals psi everywhere, not just on the boundary. So in particular, it obeys the boundary condition. And it obeys the boundary Dirac equation. So the reason this solves the complete Dirac equation is that, well, all the boundary derivatives go away because I assume psi parallel obeys the boundary Dirac equation. So we're left only with x1 derivatives. And the x1 part of the Dirac equation is also satisfied because I gamma 1 psi is psi, that was part of what we assumed. And then I've chosen so that d1 psi is m psi. So we're actually separately obeying both the part of the Dirac equation in the x1 direction and the tangential part of the Dirac equation by factorizing psi as an exponential of x1 times a parallel solution of the Dirac equation that obeys this condition. Now, if m is positive, this solution is highly unnormalizable, and so it's not interesting. But if m is negative, then it's exponentially localized near the boundary. It's plane wave normalizable along the boundary. And this is what we found is one of the main characteristics of the topological insulator phase. The boundary supports a gapless fermion mode. So, in this one?
Oh, well.
I'll try to remember to use this one.
Okay.
Now, to be more precise, we started with a 4-component. I wrote the wrong thing on the next slide. We started with a 4-component spinner, but then we imposed this boundary condition. But then in our ansatz, we imposed that condition everywhere. Since we imposed that condition everywhere, only 2 components were left. So what we've arrived at is a boundary localized mode that's a 2-component massless Dirac spinner. And 2 components is the sort of minimum possible in 2 space dimensions. I wrote here it was constrained to obey this, but I should have written it was constrained to obey I gamma 1 psi equals psi. Oh, no, sorry. I did write it. I've written both statements, not in the order I intended. Because of the constraints here that removes half of the modes, the 4-component fermion in 3 plus 1 dimensions gives a 2-component fermion in 2 plus 1 dimensions, which, moreover, is a massless Dirac fermion because it obeys the parallel part of the Dirac equation. So, in short, for negative n, or on one side of the quantum phase transition at n equals 0, we found a massless boundary localized Dirac fermion, and for the other side, there was none. So this is just a slightly different explanation, actually, of things you heard about from Charlie King. Now, generically, in the context of condensed matter, the Fermi energy does not pass through the Dirac point in the boundary. So the picture looks something like this. So the boundary of a topological insulator will be more like an ordinary metal than the Weil semimetals that we talked about yesterday. So yesterday I explained that for the Weil semimetal, we can arrange that there are Dirac symmetries, discrete symmetries that make it natural for the Fermi level to pass through the special point. In this boundary situation, that's hard to achieve naturally, so generically the picture will be more like I've drawn. So to summarize, we've learned that in a generic one-parameter family of time reversal conserving theories, there can be a phase transition between a phase with no boundary localized modes and a phase with a massless mode on the boundary. And I wrote that this was in a generic one-parameter family of band theories, but it's not hard to show that this is also valid outside of band theory. For that, one shows that time reversal, well, I actually did show it in my first lecture. Time reversal makes it impossible to give a mass to a 2 plus 1 dimensional massless fermion. So once we've gotten this answer, we can't change it by any small perturbations of the Hamiltonian that preserve time reversal. So the answer we've got is independent of band theory, even though we use band theory in motivating. Okay, so I've kind of finished what was planned as yesterday's lecture, and so now we're going to go on to a different topic. And that topic is that, okay, I'm jumping the gun slightly. So I just wanted to repeat something I've already remarked. I'm not explaining how to do this, but apart from adjusting a parameter in a time reversal conserving theory, you can actually naturally get massless 3D Dirac fermions because of certain discrete crystal symmetries. What happens, I think, would be slightly surprising to most particle physicists. It was slightly surprising to me. A rotation. As a relativistic physicist, you'd want a chiral symmetry to explain why a Dirac fermion is massless. But in condensed matter, you can't just assume chiral symmetries. The only symmetries you have are lattice symmetries. For example, discrete rotation symmetries. But it turns out that it's natural that what in the microscopic description is purely a discrete rotation, when you go to low energies, is a combination of a discrete rotation plus a chiral symmetry. So this can actually then happen in a natural way, and it's important, and even was part of the background for some experimental talks we've heard, such as notably by Ang. But as I said, for today we'll now go in a different direction, which will involve an introduction to some aspects of the quantum Hall effect. Starting with the integer quantum Hall effect, and eventually talking somewhat about the fractional quantum Hall effect. So the first thing I want to do is to explain from the point of view of effective field theory why there's an integer quantum Hall effect in the first place. So we consider a material that's an insulator, but more than that, it has no relevant degrees of freedom, not even topological ones, in the sense that its interaction with an electromagnetic field can be described by an effective action for the U1 gauge field A of electromagnetism only, with no additional degrees of freedom. So the parenthetical remark that there are not even topological relevant degrees of freedom might be baffling if you haven't encountered it before, and we'll explain it later. I had to make it at least as a parenthetical remark now, just to make my statement correct. So our assumption would not be true in a conductor whose interaction with an electromagnetic field can't be described without including the charge carriers in the description along with A. The whole idea of a conductor is that there are gapless charge carriers, so you can't integrate them out and get a local effective action. I should have stressed that this is a local effective action for A. So a conductor, fairly obviously, can't be described by a local effective action for A only. But more subtly, a fractional quantum Hall system also can't be described by local effective action for A only. It requires subtle topological degrees of freedom in addition. Now, let's start in 3 plus 1 dimensions. In a fully 3 plus 1 dimensional material with no relevant degrees of freedom, the effective action for the electromagnetic field can have all sorts of terms associated to various familiar effects. For example, ferromagnetism and ferroelectricity correspond to terms in the effective action that are linear in E or B. I'm not certain whether or not that's something everyone knows, so I'll just mention the following. If you solve Maxwell's equations with... Well, I can talk anyway for a moment while the screen is. So, take an effective action, which is the standard Maxwell action in bulk, but inside the material it has a term linear in A or B. What did you say? Do we have to disconnect it? Anyway, so take an effective action, which in bulk is the standard Maxwell action, but inside a material contains an additional term linear in A and B. So if you deduce from that the Maxwell equations, you'll get delta function terms on the surface, and you'll discover that the electric or magnetic field has a discontinuity when you go inside the surface. So that if it vanishes in bulk, you'll have an electric or magnetic field inside the material. So that's an effective field theory description of ferromagnetism or ferroelectricity. So I should stress that the term linear in E or B exists only inside the material, so it's integrated over the spatial volume of the material times time, in contrast to the standard Maxwell action that will be integrated over all of space-time. So these terms describe ferromagnetism and ferroelectricity. And similarly, quadratic terms in E and B will describe electric and magnetic susceptibilities and so on. So all these terms are manifestly gauge invariant in the sense that they're integrals of gauge invariant functions. The integrals are constructed only from E and B, or possibly from their derivatives. So if you wanted to describe the frequency dependence of the index of refraction, you would need terms in the effective action that involve derivatives. Now, in 2 plus 1 dimensions, there are all kinds of terms like I've indicated, but there's a unique term that's gauge invariant, but isn't the integral of a gauge invariant local density. And that's the so-called Chern-Simons coupling, which I'll call I Chern-Simons, and I've written it as follows, where M2 is the spatial part of space that's filled by a material, and r parameterizes the time. And I've written this in the most simple way as integral d3x epsilon ijk times ai times the derivative of ak. Now, this is not manifestly gauge invariant, and in fact, because it's not constructed just from electric and magnetic fields, and in fact, the integrand is not gauge invariant. You can ask what happens to the integrand under a gauge transformation, and you'll find that the integrand under a gauge transformation changes by a total derivative. So we make a gauge transformation that involves the derivative of a scalar to a, and you see, because of the anti-symmetry in ijk, a gauge transformation of ak doesn't change anything, but a gauge transformation of ai does. And the extra term that's added is a total derivative. So at some level of precision, this shows that the Chern-Simons action is gauge invariant when we integrate by parts. Since we had to integrate by parts, funny things will happen on the boundary, and that ultimately leads to one explanation of edge modes that we will get to later. But ignoring the boundary of the material for a moment, this explains, at some level of precision, the gauge invariance of the Chern-Simons action. So roughly speaking, we've established gauge invariance, but we have to be more careful because electric charge quantization with a field of charge 1 transforming like so under gauge transformations means that we should consider phi to be defined only modulo 2 pi. So we can imagine a gauge transformation where e to the phi is well-defined and single-valued, but phi is not. And given this, the previous proof of gauge invariance is not complete, because we assumed phi was well-defined in writing the formula, and we'll be more careful in a moment. But before being more careful, I want to discuss why that's the right thing to do. So logically, you could consider a theory in which one is only allowed to make a gauge transformation with a single-valued phi. But although it's logical to have such a theory, it's not the real world. Dirac showed that the Schrödinger equation of electrons, protons, and neutrons can be consistently coupled with magnetic monopoles, and this consistency is only possible because the Schrödinger equation is invariant under gauge transformations in which e to the I phi is single-valued, although phi is not. So that's needed to make the Dirac string unobservable. This is meant to be a monopole. Here's the Dirac string. And then Dirac considered a gauge transformation where e to the I phi was single-valued, but phi was not well-defined. Phi was singular along the Dirac string. And the possibility of that gauge transformation was needed to show that the Dirac string is unobservable. So it's more or less the same thing to say that you can couple the Schrödinger equation to magnetic monopoles, or that you can consider gauge transformations where only e to the I phi is single-valued and not phi. Anyway, we have microscopic knowledge that the Schrödinger equation is invariant under any gauge transformation where e to the I phi is single-valued, even if phi is not. And that applies constraints on the effective action that we would not have without that knowledge. So we want to exploit those constraints. It would be a shame not to use this knowledge to learn what it implies for the effective action. So to do this, we'll consider the following situation. We take our two-dimensional material to be a closed two-manifold, for instance a two-sphere, and we'll take time to be a circle of circumference beta. So physically, the reason for time to be a circle might be that we're computing a trace of e to the minus beta h for some beta. So since it's a little unphysical for time to be a circle, I might want to say that the argument would be longer, but we could take time to be an interval with initial and final quantum states, and we'd reach the same answer, but the explanation would be longer. So we can get a much shorter path to the answer if we consider computing a trace, which means that time is a circle. So the whole picture looks a little bit like this, although it's hard to draw. I think the battery is, failing in this. So for now, I'll use this one. So space is meant to be a two-sphere, although it could be any other compact manifold. Time runs around this way. So we possibly could engineer a quantum Hall system or space as a two-sphere, although it's not what's normally done in practice. But whether we could engineer it in practice or not, it's clear that the Schrodinger equation makes sense in that situation. So we can do a thought experiment that way. As for taking time to be a circle, that's just a shortcut for saying that what we're computing is trace of e to the minus beta h. So that's certainly physically sensible. So as I said, we might not be able to engineer it, but it's clear the Schrodinger equation makes sense. So we can use this situation to deduce constraints on the effective action for any system that can arise as an approximation to the Schrodinger equation. So the gauge field we want to consider on S2 times a circle is characterized by the following. We place a unit of Dirac magnetic flux on this two-sphere. So on the two-sphere, we'll have this condition. I should say that I'm normalizing the vector potential in a way that might be unfamiliar. So my covariant derivative is d minus IA. Without the e. So I'm writing a for what's more often called e times a. So that will avoid factors of e in many formulas. But some will look funny if you're not familiar with this. Now we're going to take a gauge field in the time direction that's as simple as possible. We'll just take it to be a constant s divided by beta, where remember the time direction is a circle of circumference beta. Now for this gauge field, we calculate the Chern-Simons action, and we find it's equal to s. I kind of recommend this exercise. And if you try to do the exercise, you'll find it's a little bit tricky. And I don't want to take the time to explain a completely rigorous version of that calculation. I think I'll just give you a word of advice if you want to do the exercise. It's easier to calculate the derivative with respect to s of I Chern-Simons than I itself. And then you can observe that I is 0 if s is 0, just because a0 is 0 and there is no time derivative. Time derivative is 0. So by using the fact that I is 0 if s is 0 and then computing the derivative with respect to s, you'll find you can do that without too much trouble. But it might raise questions in your mind, and to properly answer the questions requires a more rigorous definition of what we mean by I Chern-Simons. But we won't go in that direction today. Now, with the a we picked, with the a in the time direction being a constant s over beta, you see that the holonomy in the time direction is easily calculated, and it's just e to the is. Now, let's consider a gauge transformation where phi is 2 pi t over beta. So phi is not a periodic function of time. And therefore, this is not a single-valued gauge transformation if you think phi is supposed to be single-valued. But I've chosen it to make e to the I phi a single-valued function of time with period t. So in the real world, where only e to the I phi and not phi has to be single-valued, this is a meaningful gauge transformation. And it shifts s by s to s plus 2 pi. So as a check, the shift in s by s plus 2 pi leaves the holonomy invariant. And that had to be true because with my normalization of A, this holonomy is the phase factor when an electron is parallel transported around the circle. And that phase factor is physically meaningful, so it had to be gauge invariant. So we found in this example the Chern-Simons action is S, and a gauge transformation can act by S going to S plus 2 pi. So I Chern-Simons is not quite gauge invariant. So is it actually allowed as part of the effective action? Here we have to remember what's essentially the same fact that was exploited by Dirac in his theory of the magnetic monopole. The classical action I enters quantum mechanics only via a factor of the exponential of I times the action, well, or I times the action over h bar if you restore h bar, which is 1 in my lectures. So it's enough if the action is well-defined and gauge invariant mod 2 pi times an integer. And we found that the Chern-Simons action was gauge invariant mod 2 pi. So that was okay. And more generally, it can appear in the effective action with an integer coefficient. So the effective action can be k times I Chern-Simons, where k is an integer. And there are all kinds of other terms in the effective action, but they're manifestly gauge invariant. They're physically important, but their coefficients aren't quantized in this way. The Chern-Simons coupling is the one term in the effective action whose coefficient is quantized for a fundamental reason. Now, the point of this explanation has been to explain why k has to be an integer, sometimes called the level. The fact that k is an integer gives a macroscopic explanation of the quantization of the Hall occurrence. So for any material whose interaction with an electromagnetic potential is governed by an effective action, I effective, the induced current is gotten by varying the action with respect to A. Now we're interested in the case that the effective action is k times the Chern-Simons function. And let's consider a material that's at rest at, for example, x3 equals 0. So it's parameterized by x1 and x2. And the current in the x2 direction, we can compute from the action, and we find that it's k over 2 pi times the electric field in the one direction. So that's called a Hall current. We turn on an electric field in the one direction, but it produces a current in the two directions. The Hall current, we found, has a quantized coefficient k over 2 pi. Well, this is usually called ke squared over 2 pi. Remember, my a is usually called ea. Also, I said h bar equals 1, so h is 2 pi. Remember that h is 2 pi h bar. So if h bar is 1, h is 2 pi. So Charlie Kane wrote the formula as e squared over h. But in my units, h is 2 pi. So the quantization follows from the fact that the Chern-Simons action is not quite gauge invariant. I can guess that someone is going to ask, what about a fractional quantum Hall system? No? Do you have a different question? So remember, time is periodic with period beta. So I took phi to be this linear function of time. A gauge transformation by a linear function will shift a0 by a constant. But I chose a linear function with a coefficient, so the e to the I phi is single valued. That determined what was the coefficient of t, namely 2 pi over beta. Given that this phi, given this is phi, it precisely shifts a0 by 2 pi over beta. So in the next page, well, okay. So a0 was s over beta. So shifting a0 by 2 pi over beta shifted s by 2 pi. And since the action was s, the Chern-Simons function is s, it shifts under a gauge transformation to s plus 2 pi. People giving a lecture about this usually just say that the Chern-Simons function isn't invariant under big gauge transformations, without always taking the time to explain what that means in the case of a U1 gauge theory. I've just taken the time to explain it. So then, okay, the next important thing we did, I said, was that in this particular case, the current in the one direction is k times f01 over 2 pi. That's really a straightforward calculation from the definition of I effective. So A1 multiplies D0A2 minus D2A0, which is the electric field in the two direction, and vice versa. Or, sorry, unfortunately, oh yeah, sorry. So, okay, what I've written is the reverse. J2, which is what you get by varying with respect to A2, multiplies the electric field in the one direction. So that's called a quantum Hall current, because when you turn on an electric field in the one direction, you get a current in the two direction. And we've given a macroscopic explanation of the quantization of the quantum Hall currents for any system that can be described in the framework we assumed of a local effective action for the electromagnetic potential only. Yeah, any question about anything other than the fractional quantum Hall effect? What did you ask? Well, I'll make contact between this definition of K and other definitions. Now, I don't want to make people too uncomfortable, so although I'm going to delay a more systematic discussion of the fractional quantum Hall effect, I'll say just enough to make you comfortable as we go ahead. So, I'm going to give a short answer, postponing more till later. So you cannot, this integer should be fractional. You cannot get a fractional quantum Hall effect in a description in which A is the only relevant degree of freedom. But from a macroscopic point of view, this can happen in a material that generates an additional emergent U1 gauge field that I'll call little a, that only propagates in the material. So this little a has a field strength which is defined in the usual way, and I'll call it little f. You're supposed to think of little a and little f as analogs of big A and big F, except big A and big F exist everywhere, and they're as close as we know to something really fundamental in nature, but little a and little f only exist inside the material and are somehow generated by many body effect physics. Now, an example of a gauge invariant action that leads to a fractional quantum Hall effect is this one. For little a, I take a Chern-Simons function with a coefficient r, but I also couple big A to little a with a coefficient of 1. I won't go through the exercise of proving this, but actually you might want to think about it. You could check. I didn't give a completely rigorous explanation for the case with one gauge field, but you could check at least on the example we studied that this, with the coefficient I've given, is invariant under gauge transformations for both big A and little a, where e to the I phi is single value phi. So anyway, I've properly quantized both terms so that they're well defined. Well defined means gauge invariant mod 2 phi. I haven't written down the most general possibility. I've only written down a simple example that will lead to a fractional quantum Hall effect. Now, there's an oversimplified explanation of why this gives a fractional quantum Hall effect, which is the following. First, you argue that little a appears only quadratically in the effective action, so you try to integrate it out using its equation of motion. So it's only quadratic, so you can try to integrate it out. And usually integrating out something will give non-local effects, but here, in an oversimplified analysis, you claim it gives something local. The oversimplified analysis is as follows. The field equation for little a turns out to be that little f is 1 over r times big F. So up to a gauge transformation, little a is just big A over r, where r was the integer in the action. If you substitute this in I effective, you get an effective action for A only that describes a fractional quantum Hall effect. The action is just Chern-Simons of A with a coefficient of 1 over r. Well, the reason this happened was that since little a is 1 over r times big A, well, if you just substitute in, everything is a multiple of the Chern-Simons action for big A, but the multiple comes out to be 1 over r. So 1 over r appears where k usually does, and this suggests that the Hall conductivity is 1 over r. So this would describe a fractional quantum Hall system. And that's the right answer for the Hall conductivity. But there's clearly something wrong with the derivation, because the claimed answer doesn't make sense. The claimed answer for the effective action is a Chern-Simons function with the wrong coefficient, so it's not gauge invariant. So a correct derivation is not going to give a non-gauge invariant effective action for the electromagnetic potential big A. Here's where the mistake was. The mistake is that in general, F may have a flux quantum of 2 pi. And little f has the same allowed flux quantum. Well, that was assumed in deducing that the action we assumed is gauge invariant. And so for given A, it's not possible to solve the equation for little a, because we'd have to divide the flux quantum by r, and it might not be divisible by r. So there was an illegal step when we integrated out little a. And that's why it was because of that illegal step that that derivation gives an answer that isn't gauge invariant. So it's not possible to eliminate little a from the system and give a description in terms of big A only. But nevertheless, that procedure gives the right answer for the Hall currents. And The reason for that is that the procedure of integrating out little a is valid locally, because the constraint we discussed here is global in nature, and the manipulation that gives the whole current is local. So the naive procedure gives the right answer for the whole current, but the system has more subtle properties that can only be understood in the description with little a as well as big A. And we'll have a little bit of an introduction to those properties tomorrow. But I wanted to say this much now, because otherwise I felt you'd all be nervous when I went on with this glorious theory of the integer quantum Hall effect. Yes?
One more related factor, which is the object doesn't have to be quantized or rational or anything, right? I mean, if I just look at your average system at a slightly non-zero temperature, or even a system without a gas at zero temperature, I can get any of that.
Well, the gapless system, it's not true that you can write an effective action for A only.
But what I'm asking is, I nevertheless do want to get a volume inductance. So one part of the action, more or less, has to look like some sign of this. But then what do I add to shift it to an arbitrary value instead of just other rational values?
I'll see if I can give an answer tomorrow, but I better not try to do that on the fly. Now let's go back to a theory that can be described in terms of big A only. So then we have an integer k in the macroscopic description. But there's also an integer in the microscopic description of a band insulator, introduced by TKNN a long time ago, and you heard about it in Charlie Kane's lectures. It arises as follows, just as a reminder. We consider a crystal with n bands of which little n are filled. And we assume the system is completely gapped, say with n filled bands and big N minus little n empty bands. So, as we learned yesterday, in a two-dimensional system, it's generic to have no band crossings. We needed 3 parameters to make band crossings natural. So I've drawn this picture assuming no band crossings. So we're in the same situation as yesterday in our discussion of Weil semimetals, except that since there are no bad points, we work over the whole Brillouin zone B without removing anything. Also, of course, we're in 2 dimensions, so the Brillouin zone is a 2 torus, not a 3 torus. At momentum P, we have a space of all states and a subspace of filled states. So, to use a fancy language, H sub P is a rank n trivial bundle over B. Trivial bundle means just that if you consider all states, the Hamiltonian doesn't matter. So the space of all states is kind of trivial. But H prime P is what's called a subbundle of rank n. And the integer that we want is the first Schoen class of the subbundle, which can be defined in terms of the Berry connection on the filled bands. So the integer is the trace of the Berry connection over 2 pi integrated over the Brillouin zone. So TK n and n introduced this integer in band theory. So I've whipped through it because you heard it from Charlie yesterday, but also I essentially explained the relevant concepts here. So yesterday we defined an integer integrated around on a 2-sphere around the bad points. But today there are no bad points, and we're defining the same integer integrated over the whole Brillouin zone. And you heard a few from Charlie also. But anyway, there's an integer characteristic of 2-dimensional band theory where you integrate the trace of the Berry curvature over the Brillouin zone. So the basic claim of TK n and n is that k prime, which is the flux of the trace of the Berry connection, is the same as k, the coefficient of the quantum Hall current. So their original proof was based on literally calculating the current from first principles in terms of a matrix element of the current operator in the fermion ground state. And since they did this in band theory, the matrix element was written as a sum of single particle matrix elements over the Brillouin zone. And then they showed that the integral they got was the integral of the trace of the Berry curvature. I want to explain a different viewpoint where I will emphasize that k prime is not just a band concept, but can be defined in the full many-body theory. So what we'll do is 2 steps. First, we'll give a many-body definition of k prime, and then we will evaluate k prime in the low-energy effective field theory. So I'll also describe tomorrow another approach. essentially due to Haldane for yk equals k prime. So we consider a very large but finite sample. So I've tried to draw an L1 times L2 lattice for very large L1 and L2, but I want to imagine periodic boundary conditions. So both the 1 and 2 directions are wrapped into very big circles. So we have a very large 2 torus with this crystal on it. And we'll take lattice constants A1 and A2 in the 2 directions. So as I said, we assume periodic boundary conditions, maintaining the lattice translation symmetry. Now, of course, for a finite system, the momenta take discrete values. So P1 is an integer times 2 pi over A1 L1, and likewise for P2. And because we have L1 sites in one direction and L2 in the other direction, S1 and S2 take L1 or L2 values, respectively. Now, the ground state of the finite system, from the point of view of band theory, is obtained by filling all the states in the first n bands that have these values of the momentum. Now, however, we're going to turn on a background electromagnetic vector potential that's chosen so that the magnetic field vanishes inside the material, but an electron going all the way around the x1 direction or the x2 direction picks up a phase. So A1 will be a constant, alpha 1 over A1 L1. A1 L1 is just the length. A1 is the lattice constant and L1 is the number of sites. So A1 L1 is just the length in the 1 direction, and A2 likewise is alpha 2 over length in the 2 direction. So physically, you can realize half of this almost. So if you had one circle and put a solenoid through it, that'll generate, if the flux in the solenoid is alpha 1, that'll generate what we've indicated in the 1 direction. But physically, in the real world, you can't simultaneously do this in the 1 and 2 directions. But the Schrodinger equation is consistent under this situation, so it's good for a thought experiment. So we've arranged the phase picked up by an electron that goes around the x1 or x2 direction is e to the I alpha 1 or e to the I alpha 2, and therefore up to a gauge transformation, the range of these parameters is from 0 to 2 pi. Now, in band theory, the effect of turning on the parameters alpha 1 and alpha 2 is to shift the momenta of the electron. So they no longer are what they were before, but rather there are these shifts by alpha 1 or alpha 2 in the numerator. And as a check, you see that if you make a 2 pi shift in alpha 1 or alpha 2, you get back the same allowed set of momenta after shifting S1 or S2 by minus 1 to compensate for a 2 pi increase in alpha 1 or alpha 2. So the band spectrum is really invariant under a 2 pi shift in alpha 1 or alpha 2. So for any alpha 1 and alpha 2, from the point of view of band theory, we fill all states in the first n bands with these shifted values of the momentum. And that gives the ground state. Now we're going to think of alpha 1 and alpha 2 as parameters that can be varied adiabatically. So since they're defined mod 2 pi, they parameterize a torus that I'll call B hat. B hat is a sort of rescaled version of the Brillouin zone B. It would have the same shape as the Brillouin zone if L1 equals L2, but otherwise it's a kind of anisotropically rescaled version of the Brillouin zone. But anyway, B hat is a 2 torus that you should think of as a macroscopic analog of the Brillouin zone. Since Berry's construction is universal for adiabatic variation of parameters, we can construct a Berry connection A hat over B hat. And it has a curvature that I'll call F hat. A hat is a connection that can be used to transport the ground state as the parameters alpha 1 and alpha 2 are varied. All we need to know to define it is that the ground state is always non-degenerate, as alpha 1 and alpha 2 are varied. And that's generically going to be true even outside of band theory, because as we learned yesterday, you have to generically vary 3 parameters to make 2 states meet. So as a function of 2 parameters, more or less for any system, the ground state will be non-degenerate. We don't need to assume a single particle picture to define this macroscopic Berry connection. But I should say that for the conclusions we draw to be useful, at least in the formal state. We need the gap from the ground state to be independent of L1 and L2 as they become large. Otherwise, in practice, our measurements in the lab may not be adiabatic. So when we measure conductivity, Hall conductivity or otherwise, we go to extremely low frequencies compared to ordinary microscopic constants. But in a situation where the gap is vanishing when L1 and L2 is large, a practical experiment might not be in the adiabatic region. So the assumption I made here is not true for a fractional quantum Hall system, as we'll discuss tomorrow. So the assumption we make is that the gap to the ground state has a thermodynamic limit. Now, using the Berry connection to integrate over B hat, we can define an integer. Well, remember, K prime was what we got by integrating the Berry connection over the Brillouin zone. And A hat is a macroscopic analog of the Berry connection. So I'll call this one K prime hat. The flux of the macroscopic Berry connection over this rescaled Brillouin zone is what I'll call K prime hat. But I claim that the macroscopic Berry flux K prime hat is the same as the microscopic Berry flux K prime. The reason that's useful is that the definition of K prime hat is more general. K prime was defined using band theory, a single particle description based on free electrons. The definition of K prime hat assumed much less. We assumed a gap system of some kind with the sole requirement that the gap has a thermodynamic limit. Now, to understand why K prime equals K prime hat, I've drawn the discrete points in the Brillouin zone that obey the finite volume condition. The reason I didn't draw a square lattice at the beginning, but a rectangular lattice, is that I just wanted to, well, this one is the dual lattice. So if the lattice constant is small in one direction, the quantum momentum is big in that direction and vice versa. So this lattice is kind of perpendicular to the one we started with. And now I've drawn schematically the discrete points in the Brillouin zone that obey the finite volume condition when alpha 1 and alpha 2 are 0. Now, alpha 1 and alpha 2, so this picture is a picture of the Brillouin zone, but the dots are the points that are allowed at finite volume. Now, we also have a rescale version of the Brillouin zone that is parameterized by the parameters alpha 1 and alpha 2. And you can think of alpha 1 and alpha 2 as parameterizing one of the little rectangles. So we've made the big Brillouin zone out of a lot of little rectangles. It has a lot of points that are allowed in finite volume. They divide the big Brillouin zone into a lot of little rectangles. But the macroscopic Brillouin zone analog B hat is actually parameterized by one of these little rectangles. And that's true for the following reason. In black, I've drawn the allowed momenta when alpha 1 and alpha 2 are 0. If we turn on alpha 1 and alpha 2, we shift the allowed momenta. For example, I've drawn a little red vector that is a shift corresponding to particular alpha 1 and alpha 2. But every point gets shifted by the same vector. I only drew 3 of them. And if we shift all the way up to the next lattice points, either here, here, or here, of course, we've gotten back to the original spectrum. So a shift of alpha 1 or alpha 2 by 2 pi is the shift that will bring this point to one of the next points. So the little rectangle is the macroscopic Brillouin zone analog, and the union of all the rectangles is the full Brillouin zone. Now, to compute K prime, which is the Berry flux integral for the microscopic Berry connection in band theory, we integrate over the full Brillouin zone. To compute K prime hat, we just integrate over the little rectangle. But for each point in the little rectangle, which means a particular value of alpha 1 and alpha 2, we have to sum over all the states that are allowed for that value in alpha 1 and alpha 2. And that means that at any point in the little rectangle, we sum over all the translates. So these are two different ways to organize the same calculation. In calculating k prime, you integrate over the big Brillouin zone. In calculating k prime hat, you integrate over the little rectangle, but you sum over all its translates. So it's the same calculation organized in two ways, so k prime equals k prime hat. So the original version of the TKNN formula was that k equals k prime, but we can instead prove that k equals k prime hat. And we're going to, so one advantage of that is that k prime hat is a many-body concept, while k prime was a band theory concept. But from our present purposes, k prime hat is defined in terms of the response of the system to a changing electromagnetic vector potential. So we can determine it just from a knowledge of the effective action. So k prime hat we can compute just by knowing that the effective action is a Chern-Simons function. Now, we're going to practice before we get to the special case of Chern-Simons. We're going to practice by considering an arbitrary system in which we don't really have to distinguish a quantum ground state from a classical ground state. Any system in which quantum mechanics is not important in describing the ground states. So there can be arbitrary dynamical variables in the system. I've called them xi of t. They could represent the position of a particle, or they could, for example, have 3 n components that represent the positions of n particles. But they could be anything. Maybe they could be some phases in some collection of superconductors joined at some junctions. These are literally any variables, which we assume we have some kind of classical treatment of, because the assumption I want to make is that for these variables, a classical description gives a good description of the ground state. So I've written some familiar terms in the effective action for these variables. I wrote a kinetic energy, I wrote a potential energy, and I wrote an interaction with a background electromagnetic potential of some kind. But this isn't the physical electromagnetic potential. This is just some connection, some U1 gauge field that couples to the x's. So since I used straight A for the electromagnetic potential and curly A for the Berry connection, I've used a bold-faced A for this one. And then there's a potential energy, a kinetic energy, an interaction with bold-face A, and there might be other terms with more derivatives. But it will be clear in a moment they're not important. So we're going to compute the Berry connection in the space of semi-classical states of zero energy. And classically, zero energy just means that V is 0. I want to assume that 0 is the minimum of V. And so the minimum energy state is V equals 0. Now, in our application, the reason the semi-classical approximation is valid is that we don't need to treat the electromagnetic vector potential A quantum mechanically. We can view it as a given external field. If we had to treat it quantum mechanically, that would be like saying that we could see effects of quantum electrodynamics in our quantum Hall system. But usually we can't. So normally we can treat big A classically. And that's why I'm going to tell you something that's true in general for any system that can be treated classically. So we're going to be computing the Berry connection in the classical limit of anything. Now setting V equals 0 means we'll evaluate the Berry phase not for all values of x, but only for values of x where V is 0. Since I haven't said anything about what V is, it could be anything at all. This condition could give anything at all. For example, V equals 0 might be a sphere, but it might be something else. I just do an example to think about. Now, since we're going to work in the space where V is 0, we drop the V term from the action and only carry out transport in the subspace of the configuration space where V is 0. In adiabatic transport, we can also ignore the term. By adiabatic transport, I mean we study the phase of the quantum wave function when we vary from one ground state to another. In adiabatic, but we're taking the semi-classical limit, so it will be classical transport from one point to another. In adiabatic transport, we can ignore the kinetic energy term and any other term with 2 or more time derivatives for the following simple reason. We transport from a starting point P to an ending point P prime in time t, so the derivative dx dt is of order 1 over t. And then the kinetic energy is of order 1 over t, because we get 2 factors of 1 over t here, and just 1 factor of t from the integral. So the kinetic energy term can be dropped, and likewise anything with more than 2 derivatives can be dropped. So the only term in the action we have to keep is the coupling to big A. And, well, I wrote that coupling to big A as a time integral, but it has the nice property that it doesn't depend on the particular path by which we go from P to prime. So it's integrated, it can be represented just as an integral along the path without knowing how the path depends on time. So this particular term in the effective action with one-time derivatives, we can actually remove the time from it, and it depends only on the path, not on the time dependence of the path. So that's what I've indicated here. I've written this term in the effective action in a way that only depends on the path and not on how it's parameterized. Now remember, the phase that a quantum particle gets in propagating from P to P prime along a given trajectory is the exponential of I times the action, where I is the action for that trajectory. And the only term in the action we need is this one. So for us, this phase is just the exponential of I times the integral of bold-faced A along the path. But the connection which on parallel transport along a path gamma gives a phase that's the integral of exponential of I times the integral of A over gamma is just A. So what we've learned is that for any system in which a quantum ground state can be considered to be equivalent to a classical ground state, the Berry connection is just the classical connection, script A, that can be read off from the classical action. So that's how we're going to determine the macroscopic Berry connection of a quantum Hall system. We're just going to read it off from the classical action. So for the electromagnetic field in our problem, the action, well, I've written the bulk Maxwell action. It's integrated over all of space-time. And then there's the Chern-Simons action that's only integrated over the world volume of the material. Now, see, this has no time derivative, so it's like V. And we throw it away. We consider only gauge fields where V is 0, or at least it's 0 inside our material. This has two time derivatives, so we throw it away because it's not interesting in adiabatic transport. So the only term we're going to care about is this term. So to go more slowly, we consider periodic boundary conditions with very long periods in the two directions filled by our quantum Hall sample. You can do whatever you want in the third direction. A classical state of zero energy is labeled by the two angles that we had before. To compute the Berry phase, we're supposed to substitute this formula in the action and keep only the part of the action that has precisely one time derivative. And it only comes from here. If you insert this in here, allowing alpha 1 and alpha 2 to possibly be time dependent, you find that the part of the action we care about is like that. And then we're supposed to simply read off the Berry connection from the part of the classical action with one time derivative. So here's the Berry connection. The covariant derivative in the alpha 1 direction is just d by the alpha 1 because there's no alpha 1 dot term in the action. And the covariant derivative in the alpha 2 direction has a coefficient, which I've just taken. It's I times the coefficient of the alpha 2 dt. So that's the macroscopic Berry connection. And now we can calculate the Berry curvature. We just can take the commutator of covariant derivatives, and we find that k over 2 pi is the macroscopic Berry curvature. Now, you might be slightly unhappy because of the asymmetry between alpha 1 and alpha 2 in this derivation. If you integrate by parts, you could exchange the roles of alpha 1 and alpha 2. And adding a total derivative term to I prime, which you'll get if you integrate by parts, will change the formula for the connection, but it won't change the curvature. That's a fact you probably know from reading about a particle in a magnetic field in classical and quantum mechanics. Now remember, the integer k prime hat is supposed to be the integral of the macroscopic Berry flux over the, I wrote the Brillouin zone, but it should be the modified Brillouin zone b hat. So we can just compute it now. K prime hat is the integral from 0 to 2 pi d alpha 1 d alpha 2 of f hat over 2 pi. But we found that f hat over 2 pi was k over 2 pi, so the integral gives k.